Hoi! Dr. Damo here, and today we're going to talk about Project Esky. One of my dreams has always been to have an XR system that can give me desktop functionality with augmentations that I can freely interact with. In order to achieve such high-fidelity XR interactions and content, usually we would use industry-standard XR head-worn devices. These devices are capable of high-fidelity immersive experiences with minimal setup times, but are relatively expensive, closed source, and with a limited field of view. On the other hand, alternative XR display hardware is available in open source domains at a cheaper cost, making them more ideal for such a hobbyist project. However, these devices produce XR experiences at a reduced fidelity, as many of the technical software advancements available in industry standard headsets and closed source software frameworks are missing. Morgan is one of the earliest works, and while it handles optical on distortion, is incompatible with non-legacy hardware, and is missing all of the other required features. Monado is an excellent open source XR compliant driver supporting non-legacy hardware and optical on distortion. However, while it does provide head and peripheral tracking support, there is no head pose prediction, no temporal reprojection, and no between sensor calibration pipeline. The Elixir testbed is the closest related work, satisfying nearly all of our requirements for high fidelity XR experiences. However, it lacks a mean of calculating the between sensor extrinsic parameters required for a high fidelity XR experience. We introduced Project Esky, a complete open source software framework for developing XR applications and experiments on any display and tracker combination that addresses the shortcomings of related work. We do this by doing the following. For step 1, we first need to represent the distortion optics of a headset. For this we have 3 techniques. The first is a simple 2-dimensional calibration pipeline, where we use a stereo camera to obtain a series of distorted gray codes through the headset to get the per pixel depth of the optical combiner. Then, we use the results from the captured depth to fit a third-order polynomial for rendering. The second approach that can be used to represent the optical distortion for rendering is a 3D space calibration by leap motion, where a virtual representation of a screen image is overlaid on a captured real-world screen, with the optical configuration jittering until a solution is found. Esky reads the results from the calibration for the rendering purpose. Finally, we can always simplify this rendering pipeline further by simply feeding a lookup texture which modifies an input rendering image into a real-world space result. By simplifying the rendering pipeline, we are able to use any optical representation just by calculating its lookup table as a texture. The second thing we need to do is to calculate extrinsic parameters for each sensor on the headset. We have 2 methods for this. The first is an interactive technique involving the user aligning a real-world hand against a virtual image. We can then calculate the delta between the 2 hand poses as a series of points. The second uses fiducial markers detected by all tracking sensors, computing the relative transforms. The last and most fun step is loading up the game engine with Esky's integration and copying and pasting your calibration results. Check the QR codes for more info. Under the hood, Project Esky is comprised of 3 intercommunicating components. The first is the tracker thread and head pose predictor. Esky's other core component, the high-level API, which can be considered a mediator between the game engine and low-level components, receives the predicted head poses and uses them for rendering, sending the rendered frame and time step to our final component, the asynchronous renderer pipeline. The pipeline receives projected head poses and calculates the delta pose to reproject the currently rendered frame to the current timestamp. Our temporal reprojection technique is a very simple planar approach, which is as follows. We first calculate the delta between the pose of the initially rendered frame to the current timestamp, resolve the lookup for undistortion, and project the depth probe along the Z forward axis of the initial frame from screen space to real world space. We calculate the ray from the initial pose origin and the projected depth probe as vector d, calculate the ray from the final pose origin O, and a second projected depth probe as vector v. We then calculate the intersection point between ray d and v as time t, and obtain the newly reprojected point as v times t. The result of all this effort is a render pipeline that's able to render correctly registered images, despite rendering and tracking latencies. Note the difference in visual quality when the reprojection is enabled and disabled. The complete system is so powerful we can run on much weaker hardware but still achieve the same high fidelity. But don't you want to see Esky in action? Guess you're gonna have to check out the live presentation. Finally, the big mission behind Esky is open source XR for all. For any further questions, please reach out to us at the North Star Discord.